Hello. Today I am going to talk about quality control for resting state and task FMRI in SPM. I do not have any conflict of interest to disclose. SPM is one of the major softwares for FMRI data analysis. It has some unique functionality such as dynamic causal modeling, so that it is still a very popular software for FMRI data analysis. It has a very good computer interface so that one can use batch mode to process the FMRI data very easily. It can also generate output figures after each of the steps. However, this output figures usually is not sufficient for the purpose of quality control. Today, I am going to talk about what I do for quality control when I use SPM. First, some general principles. On the left side, I have outlined the major steps for FMRI preprocessing. And my point is, when we perform quality control, we have to perform quality control before and after each of these steps to ensure that this preprocessing can be done properly. Second, there are in general two ways to process the data. One is that within each subject, we can perform this every step of the preprocessing sequentially, and then we perform group level analysis across subjects. Another way is that for each of the steps, we can perform it across subjects. I feel that the later one is better for the purpose of quality control, because we need to check the output across subjects after each of the steps. It is very important to consider what are the common factors that may give rise to bad outputs, so that we may need to change the settings and to start over this preprocessing step. And also, we need to consider the distributions of some outputs to determine some criteria, for example, head motions. This brings to the third point, is that we really need to consider the whole distributions across subjects to determine some of the thresholds, for example, to remove subjects. Particularly for head motion, we need to consider the distribution of hand motion across subjects and then we determine a threshold to remove subjects. If we are studying some very special sample, for example ADHD, we may change the threshold according to the whole distributions. Quality control can be categorized into three categories. The first is before any of the preprocessing steps, we need to check the quality of the data. It includes the quality of the image, but also the image parameters and task designs. Performing initial data quality control is usually overlooked, but it becomes more and more important when you analyze data from some online sources, for example, OpenNeural or ADNI. It is really important to check the data quality before you perform any of the data analysis on those datasets. So for the image quality, you need to check whether this image are cover the whole brain, or whether there are some artifacts or lesions in any of the individual's brains. And also, you need to check the imaging parameters to see whether those parameters are consistent across subjects. It actually happens quite often that those imaging parameters, such as number of images, voxel size, TR, and so on, may vary greatly across different individuals. And for task FMRI, you also need to check the task design to see whether those task design are consistent across individuals. For example, the stimulus onset or the durations of blocks may vary across different subjects. In SPM, you can use check registration functionality to plot an image into three different views. In this case, chronal, sagittal, and axial views. You can also save this output as an image so that you can go over all the subjects very easily. I think that usually it is sufficient to use this plot to check the quality if the quality is not too bad. And of course, if you identify that the quality is really bad, or you see that there's a lot of subjects that have quality issues, you may choose to plot more slices from different views so that you can identify those quality issues. In this case, you can see that on the edges of the image, in the frontal lobe, or on the edges, you can see that some quality issues, which can only be shown when you plot multiple slices. And from imaging and design parameters, It is also will be helpful to plot the data from cross subjects. Here I show the data from the FMRI QC project. I plot each of the imaging parameters for each of the subjects. Here each bar represents one subject. And you can see some of the parameters actually vary across subjects. For example, the number of time points it varies in the set resting set 6. And also, surprisingly, the voxel size also varies in this set. It is very important to consider these variations and maybe consider removing certain subjects if these parameters are different from other subjects. And also, it is very common for task designs. For example, the on-site time or the durations of time may be varied across subjects. You really need to plot those data across subjects rather than assume that those parameters are the same across different subjects. The second part of the quality control is about checking the spatial correspondence between the images. It includes images from individuals to the common template, or between the functional image to the anatomical images. Checking the spatial correspondence between brain images needs to be performed at each step of the spatial preprocessing. Before any of the preprocessing, we need to check that whether individual's functional or anatomical image was roughly aligned with the template in MNISpace. It is a very important step to ensure that the co-registration between functional and anatomical image or the segmentations will be performed correctly. And after each of these spatial preprocessing steps of segmentation or co-registration or normalization, we also need to check the output to ensure that those image registration are performed correctly. In SPM, we can use check registration functions to display multiple images. We can also use overlay contour or overlay colored images to overlay one image over another image so that we can check whether those two images are aligned correctly. To check the initial positions of a subject's data, we can use the SPM check registration functions to show the image from one individual subjects with the template in the MNISpace. Here it shows is a good example that the subject's individual image is roughly aligned with the template. But it is also possible that the image was scanned in different directions, in this case rotated, or maybe the range was set in far from this functional image. In this case, this subject's image may not be aligned well with the template. This may not be good because in later steps, in segmentation of functional structural co-registration, those processing may fail. In these scenarios, we may need to manually set a range or rotate the image in order to better perform later processing steps. And here is another example of the functional images. On the left side, it is a good example that this functional image of a subject is roughly aligned to the template. And on the right side, the functional image appears to be upside down, and the range is also way off from this anatomical template. In this case, we have to manually set the range, otherwise the co-registration may fail in the future steps. After segmentation, we can overlay the segmented tissue types of gray matter, white matter, and CSF into this anatomical image to check the quality of the segmentation. Here is a good example because the initial position of this anatomical image was roughly aligned with the template. So in this case, the gray matter, white matter, and CSF was segmented correctly, so that you can see that those are corresponding with this, the original anatomical image. And here is a bad example. In this case, the original position of the anatomical image was not the same as the template. Here it was rotated. And you can see that the output segmented image was also not capture the correct gray matter, white matter, and the CSF. If this happens, we have to go back to manually set the range and to perform the segmentations again. Here are some more results from the segmentations. I feel that it would be very helpful to show the results in MNIST space so that we can check these results across different subjects. On the left is a good example that the brain tissue can be correctly classified into gray matter, white matter, and CSF. And the remaining two subjects have some issues. For example, in the middle subject, you can see that there's no gray matter tissue classified, which is supposed to be red. Most of the regions was classified as CSF. And on the right side, you can see that there were missing tissues on the back of the brain, and also there's no classification of the CSF regions. It's noteworthy that these quality issues is difficult to be spotted on the raw anatomical images. So it will be very helpful to show this segmented image to spot those quality issues. And after functional structural co-registration, we also need to check the correspondence between the functional image and the anatomical image of the same subject. Here is an example that the initial position of this functional image was upside down. So the results show that the anatomical image and functional image was still somehow co-registered, but actually it's not the optimal correct position, right? It was stuck in the local minima. So only if we manually set a range of this image, on the right side you can see that those two images was co-registered correctly. And after normalization, the functional images of all the subjects are aligned into the MNIST space. So it will be very helpful to check the registration of the normalized functional image with the template. And we can show this across different subjects to see the variability of the normalization across different subjects. It will be also helpful if we can make movies across different subjects to show those differences. And the last part of the quality control is about the temporal anomalies in the FMRI data, which is usually due to hand motion or other physiological noises. The main goal of the temporal analysis is to evaluate whether the FMRI signals are contaminated by hand motion and some other physiological noises. For resting state, it is particularly important because usually we study functional connectivity between different brain regions. Therefore, those common artifacts may generate spurious higher correlations, which is not what we are interested in. So therefore, we need to check whether this pre-processing step can effectively suppress those artifacts. For task-based fMRI, usually we have a task design, and we want to study whether those brain signals are correlated with the task design. Therefore, we want to check whether the hand motion or physiological noises are also correlated with task design, which is not desirable. For movie watching, usually we are interested in some highly correlated brain activity across different subjects, which is also called intersubject correlations. Therefore, we are also interested in whether hand motion or other physiological noises, whether those noises are consistent across subjects. If they are consistent across subjects, they will also contribute to this intersubject correlations of brain activity, which is not desirable. So we can plot a lot of time series to verify their correlations. So firstly, we can calculate global signals, which is the averaged signal in a functional image, and we plot it against time. Here we see that there is a spike in the time series, which cannot be attributed to brain activation because brain activation cannot generate global changes. We can also calculate the pairwise variance between each pair of consecutive images. If the brain moved between each of the pair of images, you can see that there are a large spike of variance changes in that time points, so that you can see there is a spike here. To verify whether this is due to hand motion, we can also plot this rigid body hand motion parameters here, and also the frame width displacement on the bottom. You can see that the rigid body parameters shows sudden changes at this time point and then gradually decrease. This is not a spike, but when we calculate the frame width displacement, you can see that there is a spike here, which may introduce changes in variance in this plot, and also the changes of the global signals here. So we can also plot the white matter and the gray matter signals in the functional MRI data, because we typically consider those signals are noise. And we can see that the white matter signal here also shows similar trend as the rigid body parameters, which shows a sudden change of signal strength and then gradually decreased. We can also calculate the temporal derivative, or the differences between each consecutive images. We can see that those spikes also showed up, which is corresponding very well with the hand motion frame-wise displacement and the changes of variance in these time pairs. So this shows that this hand motion may contaminate the signals in FMRI signals. And the question becomes that whether when we perform the pre-processings, whether we can remove such kind of contaminations. So in this case, we performed regressions using, for instance, 24 hand motion parameter models. After that, we can see that we plot this global signal and also the pairwise variance signals again after preprocessing. And you can see that those spikes disappeared from this global signal, right? And also in the time pairwise variance plot, we also do not see that spike at the time points around 50 here. We can still see a small spike, which means that not all the spikes can be removed, but a lot of the spikes have been removed. So to further, we can calculate the correlations among those time series, right? And then we can verify the correlation between the globe signal or the pairwise variance with other signals and the before and after preprocessing. And it is particularly interesting to see this time differences plot correlations. And you can see that before preprocessing, the pairwise variance time series is highly correlated with the frame-wise displacement and the temporal derivatives of the white matter signals, which indicate that those hand motions will concatenate the time series of the FMRI data. But after removing subject preprocessing, you can see that this correlation no longer exists. So it means that it is very efficient to remove hand motion effect using, for instance, 24 model. Even though this, you can see that this frame-wise displacement is actually very high in this time point. By some criteria, usually this subject may need to be removed. But actually, they showed here that the for instance model actually is very effective to remove such hand motion effects. So for task FMRI data, in addition to all the time series plots, we can also plot the task designs. In this case, we use FMRI QC dataset of a task design, which is an event-related design containing two conditions. One is a task condition, another is a control condition. Here we can plot the task design, and we want to examine whether this task design time series will be correlated with the rigid body hand motion parameters or the global signals. We can also calculate the temporal derivatives of task design in the bottom. We can also examine whether these time derivatives of task design are correlated with the pairwise variance plot or the frame-wise displacement. So for the correlation matrices among our time series, we can see that the task design, neither the task design nor the derivatives of task design were correlated with the global signals or hand motion parameters, which means that the hand motion may not be relevant in this case and may not be affecting the estimates of task activations in this particular task and the subjects. For a movie watching dataset, we are more interested in whether these hand motion parameters are consistent across different subjects. So we can plot this time eye movement parameters or frame-wise displacement across different subjects. So we have two dimensions. One is time, another is subject, or one is a time pair, or another is subjects. By doing this plot, we can verify whether this head position parameters or head movement parameters are consistent across subjects. In this case, we see that there's not much of correlations or similarities across different subjects. I think that the frame wedge displacement may better represent hand movement in this case, and we can calculate the intersubject correlations of the frame wedge displacement. In this case, it is very, very low, indicating that the hand motion may not be affecting intersubject correlations of different task activation estimates. Lastly, in addition to consider removing time points or removing subjects based on some criteria, it is important to consider this issue as a whole, to consider the distributions of head motions across different subjects. I feel it is very important because whenever we have a predefined threshold, it is supposed to remove only a few subjects or only outlier of subjects. Therefore, I feel that it is very helpful to plot this distributions of hand motion parameters across different subjects, so that we can verify whether this removal is actually justified, or if it removes half of the subjects, and that may not be appropriate threshold to be used. And also, we also need to be considered, for example, if we have a different group of subjects, we need to consider whether those subject different groups may have different characteristics or distributions of hand motion profiles. For example, if we studied children or children with ADHD, they must have much larger hand motion in general compared with classical controls. We need to consider that, and then to determine a threshold to remove subjects. And also, even though we can use a certain threshold, we may still introduce some bias that may end up with removing more subjects in one group but not the other group. So all of those need to be considered, and maybe in the group level analysis, we have to also include those parameters as a covariance to further control for those kind of artifacts. To summarize, the sample size in an FMRI study become larger and larger, and it becomes increasingly important to do a quality control because the data are usually from somewhere else that are not collected by the researcher themselves. Therefore, it's always good to look at the data before you process the data. And also, the quality control is not only for identify specific time points or artifact or remove subjects. It is also help to ensure that all the pre-processing steps are performed properly. Therefore, we need to perform quality control systematically after each of the pre-processing steps to ensure that this processing can be run smoothly. Also, it is very difficult to predefine a certain threshold to remove subject or time point, because we know that those data qualities or sample characteristics varies greatly across different sources or samples. Therefore, we need to check the overall distribution of these characteristics in order to determine a threshold to remove subjects. And last but not least, I would like to remind everyone that being more stringent in quality control does not always result in a good result, because it may also introduce bias in terms of you select some certain subject to include in your analysis. So therefore, more stringent does not always equals to better results. You always need to consider this, balance the data quality and also the sampling strategy in order to achieve your research goal. That's all. Thank you for your attention. I would like to thank all the lab members in our lab, especially Dr. Bharat Biswal, and also would like to thank all the collaborators and funding sources. The paper that describes these protocols for quality control can be found using this link. Thank you.